This is a Python video about Gauss's law. And I've done something like this before, but let's just jump into it. What I want to do is to model Gauss's law in Python visually. It's going to be so awesome. Okay, but let's talk about Gauss's law first. Gauss's law says that if you calculate the electric flux over some closed surface, that's proportional to the charge inside of that surface. And so what you would use this for are in cases of extreme symmetry. If you put a point charge right there and you make a Gaussian sphere and the point charge is at the center, it's very easy to integrate over the electric flux over that surface because the electric field's magnitude's constant and it's always perpendicular to the thing. And so we calculate flux as the electric flux dot n hat. N hat is a unit vector perpendicular to the surface. So in this case, they're always in the same direction. So that's easy. And then the area integral is easy. So it's easy to do. But what if I want to move the charge over here? Then it's not easy to do, but it still works. Okay, so we're going to build a 3D Gauss's law model in Python, and we're going to calculate the flux for non-simple situations. It's going to be so great. It looks so pretty. Okay, so what we need to do is to build a model for a sphere. So imagine that I have a sphere, and I'm going to break this into little pieces of area like this. Okay, so if I do that, then I can calculate the electric field at each one of these areas, and then I can calculate the flux of each area, and then I can add up all the flux. But my first problem is, how do you make a surface of areas that make up a sphere? It's not trivial. Okay, I've done a cube before. It's a little bit easier, but more complicated too. Okay, so this is what we're going to do. I'm going to use spherical coordinates. So here's my x-axis, here's my y-axis. Let's just remember how spherical coordinates work. So here I have some position r, I have the angle theta. I project this down into the xy plane, and that's my angle phi. So I have x is r sine theta, right? Because I need to project down to the x direction. Cosine phi. Y is r sine theta sine phi. And then z is r cosine theta. And so I'm going to use r equals r. It's going to be constant because I'm in the surface of the sphere. Okay. So the question is, how do I move around a sphere to make the surface? Well, I'm going to make theta go from 0 to pi, right? Because that's here down to there. Phi is going to go from 0 to 2 pi, because that's all the way around the circle. But I want to make these, if I just put areas around there, I need to find the area element, right? And so I need to change the spacing of these things as they move around. And I need to, I don't really need to change the spacing, but I do need to change the area. So the area element remember the length element in the theta direction, okay? It's just part of a circle. So this is going to be equal to r d theta, right? That's the arc element of that circle. So that's my length element. My length element in the phi direction, since I project this down, my radius of my circle is actually r sine theta. And then I have this piece times d phi. Okay, so as I change, in particular, as I change the angle phi, I need to consider this sine theta term in there too, because then I can calculate dA as dl theta dl phi. Okay, we got a bunch of work to do. So we're going to make our sphere first. So let's do that. And then we'll come back and we can calculate the electric field, and then we can calculate the flux. So here we go in Python. You know it's going to get serious because I took my glasses off. That means this is serious stuff. Okay, so I have here an empty thing. I printed that just to get things working. Let's say r equals 0.1. I don't know. That's the radius of my sphere. We're just going to make the sphere. So theta is 0, phi is 0. We're going to need to go back to Cartesian coordinates because Web v Python uses the Cartesian coordinates. Okay. Now I need to get my d theta and d phi. What's my step size? So let's say d theta is going to be equal to pi divided by 16. I want 16 pieces around there. And then d phi is going to be 2 times pi divided by 32, which is going to be the same angular size. It doesn't really matter. You can have those whatever you want. Okay, so I just need to make a double loop. I need to make a double loop to go around my list, my area. I need to go over the theta direction and the phi direction. Let's do the phi direction first. So I'm going to say while phi is less than 2 times pi, that's going to go all the way around the circle. Now I'm going to go around the theta direction. So in order to do that, I'm going to need another loop, but I'm going to need to reset theta 0, and then while theta is less than pi. And then let's just print theta phi, just so you can see how it works. And then I'm going to increase theta. So theta equals theta plus d theta. And then I'm going to increase phi. Phi equals phi plus d phi. So this should go all the way around my sphere and print everything. It may not work. I always get those loops messed up, but okay. There. I got all the angles. So that's good. I don't want to print. So what I want to do is to, I'm going to go around and put a sphere at each little location, just temporarily. Now let's do a cylinder, okay, and then I'll fix it. So what I'm first going to do is to find the vector location of each one of those spots that correspond with the r and with the theta and the phi. So I'm going to call it RT. It's a vector. Here's my Cartesian coordinates. R times sine of theta times cosine of phi. That's my x-coordinate. R times sine of theta times sine of phi. That's my y-coordinate. And then r times cosine of theta. So that's my coordinate location. You can't even see that because I am dumb. Right there. Okay. So what I want to do before I increase my value of theta right here, is this big enough? It's going to have to be big enough. Is to, let's see, wait. There we go. Okay. I'm going to put a cylinder there. I'm not going to give it a name yet. So cylinder is an object in Python that has the properties of position, which is the starting point of that, and then the axis is the vector from the starting point to the end point, and then the radius is the radius. So let's say the position is going to be vector RT. The axis, let's just put the axis right now as vector, let's put it in the z direction, no, the y direction, 0, r over 60, 0. And then the radius, let's just put as r over 30. I don't know. Let's just see, because we're just trying to make sure that things are working kind of. And there you go. Okay, so I do like that a lot. So there's all my cylinders. They're not in the right direction. I do want to use these cylinders because, that is pretty cool though, because they have, I can rotate them so they're always perpendicular to the surface, right? And so then I can use their axis as the n hat. That's what I want to do those for. Now the first thing I want to do is to get the right size. I want to get the right size of these. So up here, I'm going to calculate dl theta. That's my length in the theta direction. It's going to be r times d theta. Theta. And then dl phi is going to be equal to r times sine of theta times d phi. Just like I said on the board. Okay. So my area of that is going to be dl times d phi. So let's call that a small, just for now. It's going to be dl theta times dl phi. I need that to be true, right? And if that is the same as the area of my circle, I can calculate a radius. So let's call this r small. It's the radius of my cylinder. It's going to be equal to, well, pi r squared is going to be this. So I can take the square root of a small divided by pi. And that's going to be my radius. So down here, I'm just going to call this r small. So they do not all have the same size, right? And again, I'm blocking you with my big old dumb head. There you go. Okay, so I calculate the area, I calculate the radius from that area, and they're all different. So let's run it and see what it looks like. with different sized areas. Okay, so now you'll see up here, the areas are smaller than over here, right? Because the angle step size is the same. But now I need to rotate all these spheres so that they make a sphere. That's easy to do, right? Because the axis, all I have to do is say the following. Let's say I'm going to make it a little bit skinnier. Let's say r over 100 is the thickness. And then if I take a unit vector in the direction of its position, then it will always be oriented away from the origin. So I'm going to multiply this by the norm of RT. So norm is a unit vector in the direction of RT. I feel like my text is too small, but I'm going to keep going. Look at that. Is that not just nice? There's my cylinder. That made my sphere. Okay, there are gaps up here, and that's fine. So we need to do a couple things. The first thing I'm going to do is I'm going to make it a little bit clearer, right? Because here you're inside the sphere. I mean, we could just stop here and we'd have a great time, but we're going to keep going. So I'm going to make them a little clearer. I'm going to put the opacity at opacity equals 0.3. And let's do this color equals color.white. I'm going to put that in there for a reason that will make more sense later. But now they're just going to be partially clear. They're see-through. So you can see through the thing. Whew. Okay. Now what I want to do, it looks like it's working. Let's go up here and say area equals an empty list. And what I want to do is to add all these cylinders to my area. Oh, I'm going to do something else up here. Let's add another property, not just the color, but I'm going to say dA. The area of the piece is going to be dl theta times dl phi. I'm going to use that. Okay, you can add properties to an object like that. So here I'm going to say area equals area plus. So I'm going to add all these cylinders to a list so that I can use them again later. And that won't do anything, but let's just run it anyway. I haven't saved this yet. I had saved as print1. I'm going to give you the code. Don't worry about that. Okay, run it. Okay, so nothing new happened. Now what I want to do is I want to calculate the area of my thing. See, you notice these overlap a little bit, right? But that's fine. Each one of these areas should have the correct area, even though because they're not, my area elements should be these weird shaped squares, but you could do squares and they would still overlap, but it's harder to orient the box in Python, whereas the cylinder is very easy to orient the box. Okay, so let's go down here, and what I want to do is to say A equals 0. I want to calculate the area of my thing and see if it's the same as what I had before. So down here, I'm going to say for A in area, right? This goes through my list of area, and it calls each object A. All I'm going to do is say A is A plus A dot dA. So A dot dA is that area property for each cylinder. I'm going to add to the total, and let's print it out. So let's say print A equals A. And then I'm going to print another one. Print A equals, I know the area of a sphere should be 4 times pi times r squared. And you can't even see that. But let's see if that does indeed work. Okay, so it's pretty much the same, right? I do have the area of a sphere. That's a good thing. Okay, so now I have my area of the sphere. Let's jump back to the board and talk about how we're going to, I'm going to put a charge here anywhere, and I want to calculate the electric field at every point on the sphere, and I'll plot an arrow for that. Okay, so let's go to the board and talk about how we calculate electric field at all these different points. So I'll put my glasses on. That means I'm back to work. So we're not going to do Gauss's law yet. We're just going to calculate the electric field. So here we have our observation locations. I'm just going to draw them as spheres. And here is a Q. So I have this RQ is the vector location of that charge. And this is RO, the observation location, where I want to calculate the electric field. So I need to find this vector, R. So R is the vector RO minus RQ, right? So this is not at the center, right? It's not at the origin. And then I can calculate the electric field. I'm going to actually call that just dE, because it's just due to one. Let's just call it E. E is 1 over 4 pi epsilon naught Q over the magnitude of R squared times R hat. So all I need to do is to do that for every one of these points. I can calculate the electric field, right? If I have 2 charges, which we may do, I just need to do the same thing for 2 charges. It's not a big deal. So I'm going to need this 1 over 4 pi epsilon naught. I'll call that K. I was just thinking, yeah, let's just do it as K. Okay. So let's do this back into the computer. I need some constants up here. Let's go ahead and put a charge somewhere. I could do this as a function. I'm trying to think. Yes, I'm going to. I'm going to define a function. But first, I'm going to put a charge. So let's say K is 9 times 10 to the 9th. Q is the charge value. So 1.5 times 10 to the negative 8. I'm just picking numbers here. I don't know what I'm doing. Let's put a sphere there. I'm going to call it Q1. It's a sphere. Its position is going to be equal to vector. Let's start it at the origin because we want to start simple, but we can move it. And then I need a radius. It's going to be equal to R over 60. I don't know. Color equals color dot yellow. I don't know why I like yellow. And let's put Q, a property Q equals QQ. So I'm going to associate that charge with that object. Let's just run this and see if it puts the charge there. There's my charge right there in the middle. That's nice. Looks like the Death Star. What's the core of the Death Star? I don't know. Have you seen that movie, Star Wars? Okay. So now what I want to do is define a function. So let's define a function that has 2 things. I'm going to give it 2 things. I'm going to give it a charge object. No, I'm going to give it charge location and an observation location, and it returns electric field. So def E. So I'm going to give it RQT, ROT. So I'm going to pass it those 2 things. ROT is my observation location, and RQT is my vector force location. So the first thing I'm going to do is to calculate R. So R is going to be ROT minus RQT. Right? That's just what we did. And now I can calculate ET, the temporary electric field, K times O. I need to pass to this. This is going to have to be an object. So let's call this RTQ.POS. And so it's going to be RTQ.Q. Don't let me forget that I'm passing this in weird. That's a vector, and that's an object. It's fine. But I want to do that so I can get the charge times norm R divided by mag R squared. And then return ET. Okay, let's just use this and see if it does indeed work. So what I'm going to do here, I don't really care about all the areas. I don't care about this. But I do want to go through all of my areas and calculate the electric field at that location and then put a vector there, an arrow there. So for that, I'm going to need E scale. Let's just set it equal to 1. It's going to be way too big, and that's fine. So I'm going to go through my areas, and I'm going to calculate the electric field for each one and make an arrow there. I'm just going to do it in one fell swoop. I'm not going to, and I can do this, okay? I'm not going to give it a name. I'm just going to make an arrow. Its position is going to be A.POS. It's the location of that little sphere on the sphere, the cylinder on the sphere. The axis is going to be equal to E scale times E. And now I need to pass to it my charge, which is going to be, I called it Q1. Q1, the whole thing, and then the vector location of the observation location, which is A.POS. And then I'm going to give it a color. Let's say color equals color.yellow. And that should do it, it's going to be too big because my scale is too big, but we'll just play around with that. Let's just see what happens. Too big. Okay, so let's make that smaller. Let's say 1 divided by 1,000. I'm just picking here. I don't know. I could print the electric field, but I don't really care. Still too big. Let's do 1 divided by 2 more. Too big. Wow. I guess I should print the electric field. So it's 1, 2, 3, 4, 5. So let's just do 1 times 10 to the negative 7. Okay, now we're talking. See, we do have tiny little electric field vectors there. They want to be bigger. So let's make this 10 to the negative 6th. I was so close before. Okay, check that out. So there's my charge in the center, and then my electric field vector at all those places. I mean, come on, if you don't think that's cool, then you're just wrong. Okay, now that I have that, I can calculate the flux. Okay, so I'm going to go through and calculate the flux for each one. So remember, the electric flux is E dot n hat dA. So I can do that in one fell swoop again. So let's go back over here. What I'm going to do is to calculate the flux. So d phi is going to be equal to the electric field, which is this right here. So it's going to be dot that, and then n hat. N hat is E A dot axis. Actually, it's the norm of A dot axis, right? Because A dot axis was really thin, right? Because I gave it that R times that. And so that, I need this. Okay, there. That's the dot. Now I need to multiply it by my area element, which is A dot dA. And that's my flux. Okay. What I'm going to do now is to make my circles red for positive flux and blue for negative flux. So if d phi is greater than 0, then A dot color equals red. If d phi is less than 0, so it's negative flux, A dot color equals color dot blue. So they should all be red. I have it in the center, but let's just see what it looks like. And it didn't do anything. Norma is not defined. Norma is not defined. Norm. They're all red. Check that out. Okay, let's go ahead and calculate the total flux, and just to compare that to what we expect the flux to be. So I do need up here epsilon naught. Let's calculate epsilon naught. Let's just put it right here. So there's K. So K is 1 over 4 pi times epsilon naught. So epsilon naught, I get this wrong. Let's see, epsilon naught is going to be, I'm writing on the board, 1 over 4 pi epsilon naught equals K. So epsilon naught is going to be equal to 1 over 4 pi K. Is that right? So multiply that by, yeah. Okay. So 1 divided by 4 times, oops. Oh my gosh, did I delete everything? No, it's fine. What happened? Okay, there it is. 1 divided by 4 times pi times K. Okay, so let's calculate the flux and let's calculate the theoretical flux. So here I'm going to calculate the flux phi equals 0, and I calculate d phi, and then it's going to say phi equals phi plus d phi. So I'm going to add it all up. And now let's print that sucker out. Print phi. Notice it's capital phi, right? Not the angle. Phi. And then let's print, according to Gauss's law, Q over epsilon naught equals, And this would be, what did I call that? Q1 dot Q divided by epsilon naught. Let's see if we get the same thing. It won't be exactly the same, but it should be close. Winning, winning, okay, pretty happy. But wait, what if we move the charge off to the side a little bit? That's what we want to do, so let's do that. All we have to do is go up here when I move my charge. I'm going to give it a little r over 2 in the x direction. So it's not at the center anymore. I'm going to run it. So here you'll see that we have a greater electric field on this side than on that side, and because I moved my charge. But the flux is the same. It's the total charge inside. It doesn't change where I put my charge. What if I put my charge outside the sphere? Let's do that. So let's put this at 1.5 times r. Okay, awesome. So here we have negative flux, right? Because the electric field is going over there. On the other side, we have positive flux because it's leaving. And this is wrong, right? It should be 0, and it's very close to 0. It's about -1. This was the calculation for inside the sphere. It's not inside the sphere anymore. Okay, so there you go. Let's do one more example. What if I put a dipole? What if I put 2 charges inside the sphere, a positive and a negative? So I need to make another charge. Let's put this at 0.5 r, and then I'm going to make a second charge. I'll call it Q2, and it's a sphere, the same thing. I have to have it a different color if it has a different charge. Delete, 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 delete. This is going to be -0.5, same thing. And let's make this cyan. I don't know why I made it that color yellow and I made the arrows yellow. Cyan. And then the charge is going to be negative. So the total charge inside the sphere is 0 because I have a positive and a negative. Now I do need to go over here when I calculate my electric field. I need to do it twice. Okay, so I'm going to just put that in this thing right here. I'm going to now say, no. I have that, just leave that right there. Okay, this is fine. So over here, I'm calculating E. I need to calculate 2 E's. So let's say E total, I used ET before, ED for dipole. It's going to be EQ1 A1.POS plus EQ2 A.POS. And then this is just going to be ED. That's fine. Down here I need to change this. Arrow is going to be ED. Yeah. I might need to change my scale. Okay, so we should get 0 flux. Let's just try it out. Look at that. If you don't think that's awesome, you're wrong. Okay, because that is awesome. And look how it splits straight down the middle. The flux is very close to 0. Positive flux, negative flux. Wow, that's awesome. Let's do this. Let's move my dipole so it's not right at the center. Let's just move them up a little bit just for fun, and then I'll stop. So let's give this a 0.2 in the y direction times r, and then let's put this in at 0.2 times r in the y direction also. Okay, so now, yeah, this is as cool as I thought, but that is still cool. Still gives 0 flux. Whew. Okay, so if you've seen, a long time ago I made a cube and I did the same thing with a cube. The problem with the cube is you have to deal with 6 different sides. Here we only have one-sided thing, but we have to worry about making the area elements all equal. So there you go, Gauss's law. This is amazing, love it. And if you don't love it, that's fine too. So if you want to see my electrodynamics course, playlist down below. If you want the code to this, link down below. Talk to you later, the end, bye.